You have to figure out how to create an incentive mechanism for that, one where people can be truthful to the mechanism and actually behave the right way. You have to figure out how to do this. We haven't figured this out. So that's one open question right there for you every time you deal with people's behavior. The second piece, of course, is how do people interact with a network that lost its capacity? And so that's lost some of the capacity. And it brings up the whole question of how much excess capacity does the network have? You know, so how do we measure the degree of robustness that is existing in this particular network? So this is a question that is actually a dynamic question on a network where you're asking a question of, if I perturb the capacities of the network, how much loss in throughput do I get? Okay? And luckily, Ketan is in the room, so he can, if you have any questions, you can ask him later, but this is something that he analyzed while he was a postdoc with Giacomo Como and Emilio Frazzoli and Daron Asamoglu. So the idea is this. You have, and I'm just going to give you the idea and then give you the result. So you have a network. I'm going to assume it's a directed network. It's a transportation network, and there's an incoming traffic, and there's some outgoing traffic. Okay? And the point is that there are dynamics on these networks, and they're described by the congestion. Okay? So there's a density of traffic in each link I, and it evolves like a differential equation. Okay? So the change of the rate of change depends on the input minus the output. It's what comes in minus what comes out builds up. Okay? The interesting thing here is that what comes out is not equal to what comes in. Okay? Why? Because what comes out actually is a function of congestion. So what happens in general, this is very much dependent on the physical unit that you have, and you see these shapes all the time, that when the congestion is small, essentially this is a linear relationship. Okay, what comes in comes out. Until the congestion increases and everybody starts slowing down. Okay? And you get to a certain level of congestion where everybody stops. And there's actually a breakdown in the network. And when you have that breakdown in the network, you start cascading backward to different links that are incoming to this link, and that's how cascaded failures occur, right? And so the part is modeled from the physics of the actual road. The incoming part has to do a lot with drivers' decisions. So people come into this node, and now they have to decide where would they go. Okay, so in this particular case, I have two options that I can go this way or that way. How do I choose? Well, one way to think about it is that they make that decision based on looking at the congestion ahead of them. But they, of course, could make a decision based on congestion in 3 or 4 steps because they can see that on their Google Maps. Or they can make that decision based on a congestion pricing that we inject to prevent them from taking one way or another, and we can create that dynamic congestion pricing. So this function here actually is a complicated function that we can modulate it by decisions or incentives to try to change the behavior of people and ultimately drive the system to an equilibrium that is satisfactory to everybody. So how do you do that? And that's a lot of that work that's been done. But I do want to say that quickly. I'm going to skip a lot of this stuff to say that exact analysis was needed to do all of this to understand to just assess at any given time how close is the system to breaking down. Okay? And that's not just in terms of you need the physical model and so forth. And you want to see, for example, if you perturb the capacity of these links, how much throughput can you lose? And so this was the question of robustness, and I'm going to skip that and just tell you that the result turns out to be an interesting result, and it is some sort of a min-cut result. Okay, even though these min-cut results are natural in static networks, and you would think that they may not hold for dynamic networks, a min-cut result actually does hold in this particular situation. This one is a min-cut of nodes, not min-cut of a graph. So what you do, you look for all the different nodes, and you see how you can cut that node. You see what is the cut that will remove that node from the rest of the preceding network. And the point is that you sum on the excess capacity. So it turns out that the degree of the margin of uncertainty that you have is given by the min cut on the node of the excess capacity. The excess capacity is the maximum capacity of the link minus the equilibrium capacity of the system. So the system was operating business as usual, then gets hit by a perturbation. Already the system is in equilibrium. I have some excess capacities on the path. I can compute how much I can tolerate before the system breaks down. Okay? Now that I have this information, I can begin to use the data that I collect to try to understand, well, first of all, how did people behave to get me there? And second of all, how do I modulate the preferences to change their behavior into another way? Okay? So that leads us, but the point is, I needed this expression, or I need some expression for the distance to failure that I can measure in order to assess how people are doing. So that's the part of physical modeling. It needed a model, it needed an analysis, and now we're ready to start building some data-driven models for the people's behavior. Okay? So I'm going to skip all the details of this result. And say, okay, well, our objective maybe is congestion pricing. That's not the only way, by the way, to affect people's behavior. One important way to affect people's behavior is information. Just telling them what's there, The second one is penalizing or incentivizing through congestion pricing. But certainly information is a big factor of telling people how to behave, okay? So, and where is this leading? It's leading to this, this is just a slide for selling the story. We don't have to go through it, but this is going to, but the point here is that ultimately we are going to have a data-driven city, okay? So we're measuring the data, we have an architecture for control that is adaptable, that is reconfigurable, and it changes as soon as the system is entering or entered a cascaded failure, it has to take the system to a safe mode. It's not going to be optimally performing, but it's going to take it to a mode where it's performing and then start increasing the efficiency. So the system has to be dynamically adapting. And the whole story for a smart city is understanding that particular architecture. Okay, how do we do it? There's a lot of work of understanding whether it's better to have a centralized versus non-centralized, cooperative, non-cooperative. A lot of that work we've done. I don't have time to tell you a lot of stuff, but understanding which one are more risky than the others. Some give you more performance, but they can give you more risk. And you have to understand these kinds of trade-offs. So I'm going to move on and say that if you take that selling picture that I had earlier and draw it in block diagrams, it's really about two pieces. One is creating incentives on top, and the other one is creating control strategies at the bottom. And in creating incentives, we have this idea of learning models of commuters. And that's models of people. And that's complicated. Okay? So, but in the context of commuters, so let me just make some general comments about AI first. Pause. Forget about everything I said. Let's talk about AI. Okay? And the reason I say AI, because that, if now I'm sure in India it's the same, it's definitely in China, but it's also in the United States, control theory has become AI. And so is machine learning is AI, and autonomous cars are AI, and I would say for all I care, the power grid is AI. Okay, that was a joke. You wouldn't trust it if it was an AI. Certainly, the airplane I flew into was not AI. So there is a need for this combination of model-driven sort of mechanistic modeling and unstructured systems interacting with each other. This is really where this whole thing is happening. Structured and unstructured system coming together, figuring out a way to do this. If you think about the autonomous systems, and we're very proud that in our lab to say that one of the first autonomous cars, the company called Newtonomy, is actually an outcome of Emilio Frazzori, who was one of our students and then later faculty. And I tell you, because it was part of his thesis, how to design the architecture of the autonomous system. Autonomous system was entirely driven by the dynamics of a car. Okay? But that was a very structured part of the system. What was unstructured in an autonomous car is the vision system. And what was more complicated is the integration of the vision system with the control system. Okay, and that's where a lot of the innovation of what I would call AI is. But the initial innovation, how do you build an actual architecture for maneuvering of a vehicle to do a lot of different trajectories? And that was a pure control theory thing. But we're facing this sort of space, and I think it's really an important space. And stability and safety, I mean, I would say if stability and safety are not an issue, the problem is simple. Because you basically build this thing, run it, the robot falls, you pick it up and you let it come back. Okay? And you keep trying that. And then you put a lot of people on it, ultimately you'll get something. If the system, once it falls, you can't pick it up, that's a problem. If the plane crashes, that's a problem. Right? If the car crashes, that's a problem. So safety critical systems is really important for us to emphasize. And the social component here is non-trivial, and it's giving us a lot of challenges. One, it's unstructured. It doesn't have physics. Okay? It's really run by understanding utilities. And as Sri was talking about today, the gambler's game is moving away or giving different interpretation of what rationality really means. You know? I mean, rationality in the sense of optimizing a utility, but that utility gets modulated and changed and compensated by bias. Rationality becomes a very general notion. So that's one aspect of that. By the way, people actually do change their behavior once they see an incentive. In other words, the dynamics of the system changes with the control. And that's another challenge of these types of problems. You need to understand the behavior, but you also want to learn the new incentive. So what do you do it in a context of reinforcement learning, or do you actually do it in terms of learning? That's an interesting question. It pushes us to understand this problem from a general stochastic models. But if you have a general stochastic model, well, you have all the standard issues. First of all, this is input modulated, but you have non-convexity and you have non-parametric in general. But the biggest problem that we have is robustness. Okay? Because we're worried about safety critical systems, we need robust learning. And in the 90s, there was a whole decade that was dedicated to understanding robust learning. And the answer to that is it's not very good, right? It's not easy to have a system that learns robustly, okay? There are many negative results about exponential sample complexity needed in order to actually get any guarantee in terms of what you're learning and so forth. So you need to be able to understand that problem carefully. So I'm going to revisit that problem in a minute. And high dimensionality becomes an important. Why is it high dimensional? Because it depends at what level you're going to model people. If you're going to model them at the individual level, that is an exceedingly high dimensional system, maybe very small, very low dimensional dynamics at the local piece, but you put it all together, it's very high. Or you may want to be modeling aggregates, in which case you don't know at what level you need to aggregate. Okay, so that remains a high dimensional question for you. You are interested in cascades and low probability events, and so that means that you're looking at the very high end spectrum of the system, which is also hard because there's not much data to support you to estimate low probability events. And of course, you have questions of missing data and so forth. And I think Devrat tutorial is going to solve that problem. Okay. But we found one interesting question, and I want to give you a little bit of, yes, make it quick. So jump linear systems turn out to be, so here's an example of a stochastic system that works well in the context of a transportation system. And the story there is that basically what you're trying to do is to say that people that come into the system come with different types. There are people that are price sensitive, people that are price insensitive, people that are trying to get home as fast as possible regardless, people can wait. There's different types. And in general, you don't know these types a priori. But now you observe the data and their behavior, and you're trying to understand, can I learn this sort of system from the data that I observed? So the mathematical formulation comes back to, can I learn this stochastic jump system? What makes it a jump system is that it's a linear system, but the transition probability changes according to a probability distribution. So you sample from a probability distribution and A matrix. Why is this problem not trivial? Well, because its parameterization is bad. It's not really a good parameterization. That's one thing. So always yields issues of non-convexity. Second thing is that there are a couple of things I don't know and I cannot assume I know. One is I don't know the support of the probability distribution of theta. I don't know how many A's there are because I don't know how many types the system has. So I have to learn the number of types first. And the second thing is the state space itself may be unknown in terms of its dimension. That could describe the attributes that describe these different kinds of groups, and I don't know what the dimension of that. So the general high-dimensional mathematical problem that says is that I need to learn the system, not knowing how many states I have, and not knowing how many A's I have, and not knowing any spectral characteristics of A of theta ahead of time. What is the conclusion about learning such a system? It's not possible. It's not possible. So you have to start adding some assumptions. And the question, do you add assumptions to make this problem trivial? And the answer is you can't. So you're not allowed to all of a sudden make the number of states finite, make the number of A's finite, and then tell me about the spectral dependence of A, because we turn this problem into a very simple kind of multiple regression. But that's not the problem that we have. So anyway, I don't want to spend that. That was the technical that was rejected. And so because of that, I won't get into the data. Thanks to God it was rejected, because otherwise I would have had to give a full lecture on this. But I do want to say that this is the work of one of my students who's not here, Toheen Sarkar. And the idea there, and I think the idea is really important, is that what you want to do is connect learning to the theory of approximation. Okay, so what does that mean? That problem that I described to you is not learnable, or if you like, the size of data that you need is exponential in the unknown parameters. And so you don't know the parameters and the size of data is exponential, so the problem is not learnable that way, in that sense, right? But then what is learnable? If I gave you 100 data points, you can't tell me nothing is learnable. Something must be learnable if I gave you 100 data points. And the answer to that question is some lower dimensional approximation is learnable with 100 points. Can I get that? So by lower dimensional approximation of the original process that I don't know is learnable with 100 points. And so the challenge for this theory is, can you tell me, if I gave you 100 points and some mild description on the system, namely, for example, how big the gain of the system is and so forth, can you tell me what low dimensional approximation can you get out of that system? And what is that sample complexity of that? And it turns out that that wasn't even worked out for the linear case, let alone for the jump linear case. And so, so this is the story. It turns out that the connection here is the Hankel structure. For some of you who've studied linear system theory, you know that the Hankel matrix captures everything about the system. It captures the realization, captures the approximations, and so forth. And so it comes down to questions of how you approximate the underlying Hankel with a lower dimensional Hankel. Do the singular values approximate in the right order, essentially, or not? And can you actually develop a realization and an approximation theory from this? So it turns out that the answer is yes, and I'm going to skip all of this because that's a lot of mathematics. But the point is the answer is yes. Okay, so you can do this, and this is sort of this is the LTI result here. I'm happy to talk to you about this result if you're interested. But it's not only that it's possible; it's also computable in the sense it's algorithmic. You can actually take the data and turn it into a model through computable algorithms, and so I can talk about that later on. Okay, but I'm going to move on because I'm left with it's about 10 minutes, and I want to talk about the last topic. So what I've done is I've told you that it's important that we understand the underlying physical system. From that, we can probably set up questions of how to learn people's behavior, and then from that, incentivize that behavior. But that requires us to be able to collect the data about people. And that issue itself is becoming extremely important. How do you get data from people? You know, we all had We all freaked out when we found out that Facebook has given data to Cambridge Analytica, right? I didn't freak out, actually, because I didn't think my data had any value. But some of my colleagues removed themselves from Facebook. I no longer work for Facebook. So they thought their data is more valuable than mine. I wasn't, maybe there are. I'm not sure what they have in there. Serve them right. Never be on Facebook. But the data economics is really an important question. And if you think about the infrastructure examples that I just gave you, it kind of presents a whole question about having some sort of a two-sided data market, right? In the sense that if you think of the municipality managing the transportation system and wanting to learn all of this information that I just described, you would like probably to get data from the Ubers and the Lyfts and the bus system and the taxi system and individual people and so forth. And maybe some of these agencies won't volunteer their data for you. And so you may have to enter some sort of a market to buy that data. And the question is, well, is there a market for you to buy the data, and how much would you pay for it? It's not that different, actually, from the management of energy, as Sajid mentioned. And as I said, the electrification of cars is going to be a key issue, because what is interesting about the electrification of cars is that they present a huge problem for the grid, but they also come with the solution. They come with a solution because they have the storage component sitting in the car, right? And so if everybody is charging and keeping the charge and not sharing it, that's a huge problem. But if we think of these cars as sitting in there as a farm of small electric storage, then and we're allowed to manage it, then we can solve that problem. So the problem comes with the solution comes with the problem, but it's predicated on knowing the data of that particular car. Is it going to stay in the garage until 5 p.m.? How much charge does that car need before it goes home? That's data that we need from the participants. So there's a market of data on top of the market of storage that are necessary to analyze in order to solve the problem of electrification. So, and certainly the retail market is another example that you can have. So, infrastructures are, but more so, I think data market has, beyond infrastructure, the question of data has become really important. This is a quote from the European Consumer Commissioner: "Personal data is the new oil of the internet and the new currency of the digital world." People believe that your data is really valuable, but you never get compensated for that data. If you look at data companies, Bloomberg, Nielsen, Reuters, they actually are having a hard time selling data, having a hard time with their marketing pitch. They don't know what to tell people why they should be buying their data, other than telling them, oh, you know what, Delvrat is buying my data, so Anish, you should be careful because he may beat you in squash if you ever remember. He's buying data about squash, and so Anish goes and buys the data out of fear, and then say, okay, why don't you get a 10-year engagement with us? We will give you a 50% discount. It's very inefficient and is not very systematic. If you think about 23andMe, it's actually a very interesting problem there. On one hand, this is 23andMe that you sell your genetics, and it's interesting because you don't sell, you actually pay money to give them your data. So that's already the first crime. They give you some really very insignificant piece of information about who you belong to, what your origins are. Mine turned out to be North Africa. North Africa turned out to be the whole space from the Atlantic to Iran. So I know that my genes come somewhere from Morocco all the way to Iran. I think that didn't narrow it down for me. I think if you're from Northern Europe, you actually get a better estimate. But anyway, you pay the money to get your data. No comment. But there's a feedback issue here. So actually, 23andMe in fine lines say that we will never use your data for something else, and your data will not be sold without your consent. But actually, they helped in catching this criminal in Northern California, right? And we all cheered. Wow, 23andMe helped catch that criminal. But they violated their principle that the data cannot be used. Now, we liked it the way it was used. It was a positive thing. They love to say it that way because they are going to breach that agreement. And they'd like to sell it to you first by saying we did it for the global good, right? But it's at some point, they're able to analyze your data for everything else that you didn't ask for, and maybe they'll find a rare disease that I have, sell that information to my insurance, and I'll end up paying higher insurance in order to treat myself. That I cannot control. So not only I paid money for giving them their data, I'm going to end up paying money also potentially in the future for something that they find in my data. So it's a bit of a problem. But in another dimension, what happened with Equifax data breach, again, I don't know if my data was in there, but there was 150 million individual financial data that was actually breached. And it's not clear at all that what impact that has. Contrast this, say, to the stock market when it lost 50% of its value or 60% of its value. At least we were able to make a quantification of this. And I mentioned Cambridge Analytica, so I'll keep moving, okay? So this has been an intriguing problem that Devrat and I have been thinking about, and Anish Agarwal is the person who took interest in this problem and developed everything that I'm going to say from here on, and I won't give you all the details, but let me just say a few things that are important. Why? Okay, so there's got to be a market of some sort where you can buy data. If my data is valuable, it's worth something for you. You should be paying for it. And the question is how much? So, well, first of all, a couple of things are really important to think about. Okay, one is data can be replicated at zero marginal cost. So I can sell my data to multiple people, which means that if they're competing, it becomes a problem if they both get it or one gets it and the other doesn't get it. But certainly, it doesn't cost me anything to sell multiple copies of my data. The value of data for a particular firm might be combinatorial. If you think about the example of transportation and the municipality that is managing the traffic, what data set will actually affect minimizing congestion could be any combination of the data sets that they have. Okay, and so really, at the end of the day, any combination of data that is out there in terms of Uber or Lyft or bus or taxi or individual data, right? And so the value is very combinatorial that way. And also, if we're selling data, I'm selling my data. I'm not interested. I don't really care who's buying it, but the buyers may have different objectives.